We present a method for neural rendering of human from a single image. Given a source image of a person and a target pose or target garments, our method renders high-quality image of the source person in the target settings. Our algorithm represents human bodies with the SMPL surface model. Instead of modeling appearance as color-based UV texture maps, we employ a learned high-dimensional UV feature map. We use a unit-based network that implicitly converts UV texture map to a high-dimensional UV feature map, which is then subsequently used in the pipeline. Here, we provide the overview of our pipeline. The entire pipeline can be divided into 4 distinct steps. I'll explain in more details of the steps in the following slides. The first step is UV feature extraction. We run dense post RCNN to get pixel-to-texel correspondences between the input and the texture image. Given these dense post correspondences, we extract the partial texture from the visible area of the input image. Note that this step directly brings appearance information of a person in any pose to a normalized coordinates defined by the SMPL texture. The second step is UV feature map in painting. We use a unit-based network to transform this 3-channel texture map to a full n-dimensional feature map. The third step involves feature image rendering. Given a target pose which can be different from the source pose, we render the underlying SMPL with a full UV feature map to produce a rendered feature image. Please note that this operation can be easily implemented by differentiable sampling. The final step is the translation of the feature image to a realistic image. Here we use an image-to-image translation network to perform this translation. We follow closely the design of Pix2Pix HD. Given a source and target image pair, the entire pipeline is trained end-to-end with the following supervised losses. An intermediate in-painting loss in the first 3 channels of the UV feature map, a VGG loss or a perceptual loss between the generated and the target image, a Pix2Pix HD based adversarial loss on the generated image, and finally, a face identity loss to preserve the facial identity on the cropped face of the generated and the target image. During testing, given a source appearance image and a target dense pose, a single forward pass is performed for the pose transfer. Now we switch to the results. For our main experiments, we use the deep fashion dataset. This dataset contains models with different clothing items in different poses. In this slide, we show our results and compare with the other state-of-the-art methods. For the state-of-the-art methods, we choose the coordinate-based in-painting, deformable GAN, variational unit, and dense pose transfer. It can be easily observed that our results show higher realism and better preserve identity and garment details compared to the other methods. We show some more results here. Now we show some quantitative results. In terms of SSIM, we perform similar to the existing methods, whereas we significantly outperform them on LPIPS metric. In addition, we perform user study where we compare our results with the results of coordinate-based inpainting and dense post-transfer. On both criteria of realism and appearance preservation, our method is chosen over the existing methods. For more details on the user study, please refer to our manuscript. To study the advantages of the learned neural texture over the other natural choices of texture-based human re-rendering, we created the following baselines. In the experiment no-int, we do not apply any intermediate loss to the first 3 channels of the UV feature map. The inpainting baseline consists of 2 stages. The first stage is to train a separate inpainting network for the texture map, and finally, after the convergence of this inpainting network, we trained the rendering network with the inpainted texture. Note that this method is very similar to the method of the dense post transfer. In the experiment of warp, which is the warping based method, we warp the incomplete partial UV texture map to the target pose, and then finally we apply a render net on the incomplete warped partial texture. In the experiment of warp cont, we provide additional dense pose conditioning to the render net. Here we show some qualitative results of the aforementioned baselines. The baseline IP performs well but produces smooth output compared to the other methods. Because of the lack of details, baseline warp often produces non-realistic output in both face and garment regions. When the warp-based method is provided with additional dense pose conditioning, the quality of the result increases. However, in the presence of strong occlusions, the method fails, as the translation network is incapable of performing both inpainting and realistic rendering at the same time. In contrast, our method uses a richer intermediate representation and produces more realistic image than the other baselines. Our method can be naturally extended to perform garment transfer without any further training. Here we just combine the partial texture of the body and the garment parts coming from the 2 different images into one combined texture map. This combined texture map is then used as an input to our pipeline to produce source body with the target garments. Here we show some results of our method for garment transfer. We can also perform motion transfer from a single conditioning source image. We keep the source image of the imitator fixed and use the pose from the actor of the driving video in our pipeline to create an image animation. For more results and details of our method, please refer to our manuscript. Thank you for watching.